All right, good evening, my fellow EM aficionados. It is Sunday, December 7th, the day that will live in infamy. I just realized that now. Um, and I got a video for you here. So I know ever since I did that video 2 years ago about STEM and the Fast Fourier Transform, there have been, constant barrage of requests for part two. So what I decided to do for part two, which is applications, instead of doing one whole video, I've decided I'm going to break this up into like chunks. And I'm going to do just like smaller videos discussing a specific application of the FFT, rather than one whole video putting it all in one, because I think if I tried to bite it all off at once, it's just going to be too much to chew. So we're going to talk about an application of the FFT today. And that application is accurate measurement of D spacings inside of your images. Okay. When you're doing, high res TEM or atomic res STEM or anything in that regard. Okay. So we're going to just assume that we're using ImageJ here. And everybody's going to have access to Velox or digital micrograph, although those are becoming easier to get. I mean, there's Velox Lite now, which I believe is free. But we'll just do this with ImageJ, which works fine. So I have a head of STEM image here, and so what we're looking at here is a superlattice structure of hafnium zirconium oxide, and that is encompassing these thin layers of alumina, which is the dark stuff. So the HCO is about 1.5, sorry, the HCO is about 5 nanometers, more than that actually. I think it's supposed to be like 8.5 or something. Anyways, the periodicity is about 10 nanometers. So one of the things I see often done in papers is people are trying to measure a D spacing that they're seeing in an atomic res image like this. Okay. Of course, this is a STEM image, but you can do the same thing in a TEM image too. Okay. So we scroll in here. So in the case here, what we see is a snippet of this image where the there's basically one D spacing that's dominant or prominent. If we look at some other portions of this image, like this here, there's a lot of different D spacings going on inside of this. Okay. Again, if we do the FFT, right? So we can do the FFT. Sorry, my dog is attacking my cat. We can do the FFT of the whole thing. The problem though is that we don't know where we're getting what from. Okay. So in other words, if I'm going to just crop this out here, hold down Shift, Control Shift D, duplicate without the scale bar. So now if we take the FFT of this image, okay, so as you can see, right, we got a lot of stuff going on here. We don't exactly know what set of features in here corresponds to, this, right? I mean, we could kind of guess because these spots are going to be perpendicular to the fringes, right? So we might look at it and say, well, maybe it's these, okay? But we don't really know. So what we can do instead is we can just isolate this part of the image and then take the FFT from it, okay? So I'm going to actually keep this whole image FFT for the time being. So now back here, you can see that we have a calculated pixel size of 33.58 picometers, or 0.03358 nanometers, which we're going to use later. So if I use my rectangle tool, if I click Shift, click, hold Shift and drag, okay, so I can just isolate this, then do Control Shift D, and then I just see this area. Now, one thing I can do, so I can calibrate this here, If I go to process, no, analyze, set scale, 1 pixel, the distance is 0.03358 nanometers. Okay, so the horizontal field width is about 8.13 nanometers. So now I can try to measure the d-spacing directly, okay, using a profile. So if I come over here and I draw the line tool, I can click and drag, and I can eyeball this so that I'm approximately perpendicular to the lines. I can go to analyze and then plot profile, and then I see this, okay? And I see people doing this a lot as a way to measure the d-spacing. So the problem, sorry, people are blowing up my phone here. The problem with this is that it's difficult to draw this line perpendicularly by eye, okay? The other thing too is that we're only using a line here as opposed to, I swear everything that can make noise is making noise right now. Um, the thing that's difficult about this is that we're also using only a single line of pixels, right? We want to integrate this. So one thing we can do instead is we can use a box and we can plot this. Okay. The problem though, of course, is then click live. Okay. But the problem though is this has to be perpendicular to the lines. So now, unfortunately, in image J, we can't do this with the rotated rectangle. So if I use the rotated rectangle, this is kind of a neat tool here. So right click on this and then rotated rectangle. It won't let you plot a profile from this, okay? So you have to use either a line or a rectangle. But one thing we can try instead is we can rotate the image so the fringes are either perfectly, well, let's make them perfectly vertical, okay? So we can go to image, or sorry, where is it? Image, transform, and then rotate, okay? And then we can add in some grid lines, preview, and then we can adjust this until we've got our fringes running nice and vertical. So that looks close. We can even do fractions of a degree. And again, this is eyeballing, right? But we'll go ahead and do this. So actually, maybe before I do this, let me duplicate this. Control-Shift duplicate. So we have a before and after version. And so we can transform, rotate, and there we go. Okay. So now we can use a full rectangle, and now we're integrating several pixels here, or many rows of pixels instead of just one row, and then we can plot the profile. There we go. Okay. So now, because this was calibrated, okay, we can calibrate this. Okay. So now it's the d-spacing is peak to peak or trough to trough. Okay. So we can use the rectangle tool and we can click and drag in here, and you can see over in image J where it says W, okay, that's the width of the box. So we can count now 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Again, the more d-spacings you can measure, the better. So that's, again, I believe that was 5.33 nanometers, okay? So now open up your calculator, 5.33 divided by 20, and it's telling us that our d-spacing is 0.267 nanometers. So when you're actually measuring d-spacing, keep in mind this is really only accurate to a tenth or a hundredth of a nanometer, okay? So really we should round this to 0.27 nanometers, okay? So anyways, so again, a lot of eyeballing involved with this. So now, what if instead, right, we have this image here. Let's just compute the FFT. Okay, so there's the FFT. So now, since we've isolated just this area, so these are the spots here. These are perpendicular, obviously, to the fringes. Okay, you have to identify that. But now, all we have to do is put the mouse over the pixels in question. Okay, so you can see right here. So it's saying 0.26 nanometers. Okay, you can see right here, right on the edge. Okay, so because and now it's saying so you have to measure this in the center, obviously, of the spot. So it's giving us 0.27 nanometers. Okay, exactly the same as what we were getting the other way. Okay, so because we calibrated the length in the initial image as nanometers, it's going to give us the real space distance also in nanometers here. Okay, so you can see, right, 0.27 nanometers. Now let's say, for the sake of argument, oh, sorry, my cat's trying to get in my lap. Oh boy. Come on, kitty. Come on. There we go. Oops. Okay. All right. All right. Now the cat's in my lap. All right. Let's say for the sake of argument that we didn't calibrate the scale. Let me close this, and then let me duplicate this. And I'm just going to change this to pixels, okay? So we'll go 1, 1. Oh, we'll just click remove scale. There we go. Okay. There we go. Okay. So now we don't have any meaningful units for this, okay? But we knew from back here that our pixel size was 33.58 picometers, okay? So if we compute the FFT, what we get now is we get an answer that is in pixels, okay? So you see where it says R equals 7.92 pixels. Okay, so the P is for pixels. So now we have to convert that to an actual number. So we multiply that by the pixel size. Okay, so if we open up our calculator here, so we have 7.92 times 0.03358. And again, we get basically the same number, which is 0.27 nanometers, or 2.7 angstroms. Okay. So anyways, this, in my opinion, this is always going to be a more accurate way to measure the d-spacing as opposed to doing this, right? Because this is, of course, the whole image, right? You're only sampling part of it when you do this. Of course, the other thing too, right, is you have to be able to properly identify the set of fringes that the spots correspond to, okay? So in this case, you can see, right, we have these higher order reflections out here, or spots. So those are not the ones you would want to measure, obviously, right? So you actually have higher order spatial frequencies that are contributing to this d-spacing, but the actual fundamental spacing itself is the spot that corresponds to the smallest distance. All right. Oh, kitty, I know you want to jump up on the computer, but you can't. Okay. So you have to keep that in mind, okay, when you're doing this, right? It's going to be the closest spots, okay? Doesn't matter, of course, you can measure the opposite one or the positive one, you're going to get the same answer, okay? Or you should get the same answer when you do this, okay? So that is one of the applications of the FFT, okay, is doing accurate d-spacing measurements. Okay, and again, right, whether you're doing this via FFT or you're doing this via the image itself, d-spacing measurements made inside of an image, I would not claim to be any more accurate than a tenth of a hundredth of a nanometer. Okay, which would be a tenth of an angstrom. Okay, so I would call that your error, so to say. Plus or minus a hundredth of a nanometer, or plus or minus a tenth of an angstrom. Okay, so that is the first of the application videos I'm going to be doing about STEM and the FFT. So hope you find that useful. And of course, I've got some other ones here. We got winter break coming up, so I should be able to knock out a few more of these, coming up here very soon. So hope you're having a nice Sunday evening here, and talk to you all very soon.